Hello friends, welcome back to our Control Systems Simplified series. With all the concept of stability that we have learned so far, let's start understanding the Routh Hurwitz criteria, or H criterion for short. It is basically called as the stability criterion for control system. So far we know that for a system to be stable, its poles should lie on the left-hand side of the S-plane. And for any system, if the poles are on the right-hand side, the system is automatically considered unstable. Now, if you find the location of the poles by solving the denominator polynomial, which is also we normally call it as a characteristic equation of the transfer function, then if all poles lie on the left half of the S-plane, we call the system stable. Now, for a quadratic equation, we can solve it easily. Probably even for a cubic equation, with some difficulty we can do. But as the order of the characteristic equation increases, it gets increasingly difficult for us to find the location of the poles. And that's where exactly the Routh Hurwitz criterion, in which we can determine the stability without solving for the poles. Now, just to go forward, let's consider a system with a quadratic characteristic equation, an s power n plus an minus 1 s n power minus 1 plus and so on, a1s plus a0. This is the characteristic equation of a particular control system. Now, for the system to be stable, that is to ensure that all the poles lie on the left-hand side of the S-plane, it is necessary that all the coefficients of the quadratic equation should have the same sign. All the coefficients should have the same sign. That's number one. Then there should be no missing term. This means that there should not be any coefficient with zero value between the highest power of S and the lowest power of S. Okay, zero value between the highest power of S and lowest power of S in the equation Q of S. So these two are essential if we have to ensure that all the poles are on the left-hand side. So just writing the coefficients alternatively in the first and second row of the array, starting with the first row, we form the Routh array, we normally call it as. Now let's take an example. Procedure for following this one is basically, we have the s power n minus 1, s power n minus 2. We shall form the third row with the following procedure. Now, first two rows we can always, so this is s power 1, s power n minus 1, s power n minus 2 on this side. Then the coefficients, if you write it on a Routh array, we have an minus 1, an minus 2, an minus 3, an minus 4, an minus 5, an minus 6, an minus 7, like and so on, we can go. So these two rows we can write easily. So for the third row, we have a procedure. For the third row, for bn minus 1, if we have to get here, bn minus 1 equal to an into an minus 3 minus an minus 1 into an minus 3. That is exactly what we get. Okay, so I'm sorry, this is a slightly different. So bn minus 1 we get an minus 1 into an minus 2 minus an into an minus 3 divided by a power n minus 1. That's the first procedure. Then, if you want to get bn minus 2, similarly here, an minus 1 into an minus 4, you observe the gray lines here. An minus 1 into an minus 4 minus an into an minus 5 divided by an minus 1. That's where we are starting. We're starting basically the an minus 1. So that's how this goes like this. So similarly for the next row, we repeat the same for the next row. Cn minus 1 if you want. An minus 1, Bn minus 1 minus an minus 3 minus of an minus 1 into bn minus 2 divided by bn minus 1. That's exactly. So cn minus 2 we get bn minus 1 minus an minus 5 minus of an minus 1 into bn minus 3 divided by bn minus 1. This is always the base 1, bn minus 1. So cn minus, similarly, if we go on doing like that. Now we'll continue this process till s power 0 and Routh array is completed. So we got an minus 1, an minus 2, an minus 3, an minus 4. So we got bn minus 1, bn minus 2, bn minus 3, cn minus 1, cn minus 2. So we do this until we have s power 0, starting from s power n minus 1, s power n minus 3, until s power 0, where we are getting h n minus 1, something like that. Now, we have a Routh array. This is basically what we normally call it as Routh array. This is obviously a tedious task, and with more complicated equations, we would have fed up by this time. With this, we shall now understand how we can interpret stability from this array. As per Routh Hurwitz Criterion, for a systems to be stable, it is sufficient that all the elements of the first column, this is the first column, this is the second column. So for a system to be stable, it is sufficient that all the elements of a first column of the Routh array are positive. This is one thing. If this condition is not met, we can straight away declare that the system is unstable, and the number of sign changes in the first column of the Routh array will give the number of poles that lie in the right half of the S-plane. This illustration below will give us more clear. Okay, so there is no sign change here, no sign change here, no sign change here. Okay, so no sign change. So if there is no sign change, it is stable. If sign change is there, unstable. So how to find out number of sign changes are equal to number of poles in the right half of the X-plane. Now let's take another example. Let's take this characteristic equation here. Q of S is equal to S cube plus 4S square plus 9S plus 10 is equal to 0. The roots of the equation are S is equal to minus 2 and S is equal to minus 1 plus or minus J2, okay, or 2J. This is what we normally, so we have totally 3 roots here. Minus 2, 1, minus 1 plus J2, 1, minus 1 minus J2, 1. Okay, so if the system is considered to be stable, since all the poles lie on the left half of the S-plane. So if we draw this, similarly our equation, we are starting from highest S cube, S square, S1, S0 here. And then we are writing 1 here, 4 here, 9 here, 10 here, alternatively. an minus 1, an minus 2, an minus 3, like that. So since here, S power 0 has come here, right? Now, for this, how do we get this? Okay, 4 into 9 minus 1 into 10. Okay, 4 into 9 is 4 into 9. Okay, this one minus 10. That is exactly divided by 4. That's exactly what we get, 6.5. Okay, so how do we get 10 here? So 6.5 into 10 minus 4 into 0 divided by 6.5. So we get 10 here. So here, if you see the first column, 1 positive, 4 positive, 6.5 positive, 10 positives. So no sign change from first row to first column to, in the first column from first row to second row. So the system is considered to be stable. Since all the elements of the first column of the Routh array are positive, we normally consider, let's take example 2, where Q of S is equal to S cube plus S square plus 3S minus 5 is equal to 0. We have seen it in the beginning. Since the equation has one negative coefficient, it should not miss the power of the S. anywhere, or there should not be negative coefficient. In that case, the system is considered to be unstable. So irrespective of that, let us try to solve this with our own equation. We have 1 here, S3, S square, S1, S0, 1 here, and then 1 here, then 3 here, and minus 5 here. So how do we get this? We get this 1 into 3 minus 1 into minus 5. Okay, divided by 1. That's what we get. Okay, and then from here we get 8 into minus 5, 8 into minus 5, minus of 1 into 0 divided by 8. Okay, so we get minus 5. So if we see the first column of the row, there is a change of sign in the first column. So the system is unstable, and there is one sign change because so there is one pole on the right half of the S-plane. This is exactly how we understand the Routh Hurwitz criteria helps us in understanding the stability of the system. Without solving, it's very difficult, cumbersome to solve this cubic equation. If you have S power 4, then it will be very difficult. So that way, this helps us very easily to find out the stability of the system, whatever may be the order of the characteristic equation of the control system. Hope that is clear. Thank you very much.